Welcome back to linear algebra. In this video, we're going to be considering the idea of the span of a set. Jumping ahead to the conclusion, the span is going to turn out to be a very efficient way of generating a vector space with very little information. So, considering the span of a set of vectors is going to be the most common way that we describe a vector space in everything that we're doing with vector spaces for the rest of this course. Without further ado, let me get my head out of the way. Let's jump into the definition. Consider a vector space V and some set of vectors. Written very poorly. These are in fact all supposed to be U's, but they kind of look more like V's. So let me try that again. I want set U to be the set of U1, U2, all the way through to UN, a set of vectors. U itself may or may not be a vector space. That doesn't matter. It is convenient to have a finite number of vectors in set U. Technically, this works for infinitely many, but you have to get into some calculus stuff that I don't want to deal with in this course. So we're going to deal with finite numbers of vectors in set U. The span of U is the set of all linear combinations of vectors from U. Symbolically, we can write that span of U is the set of all C1 times U1 plus C2 times U2 plus ... plus Cn times Un. For C1, C2 up through Cn, all being real numbers. And again, we're dealing with real vector spaces in this course. So real numbers is the set of scalars for vector space V, and that is important. I've got a couple of theorems I want to prove on this span, this odd-looking set. The first one is that the original set of vectors U is a subset of the span of U. And the proof there is actually fairly straightforward. It's a lot more tedious to write out than it is difficult. If I pick C1 equals 1, I pick C2 equals 0, C3 equals 0, all the way through to Cn equals 0. Well, 0 times any vector is the 0 vector, 1 times any vector is that cell. So this is U1 plus 0 plus a lot more zeros, which is definitely U1. And you can do the same thing with U2. Pick for UK, pick CK equals 1 and all other CI equals 0, and you get the linear combination that gives you UK as the result. So we can show that all of the vectors in the original set are still there in the span, which is important because that gives us that the span is non-empty. And we know that non-empty is a very useful tool for talking about vector spaces. Next up, the span of U is a subset of V. And once again, the proof isn't that difficult, but it is something that needs to be established because it's not necessarily obvious at first glance. Although not all that difficult either. Right? We know that set U is a subset of set V, so that means that U1 is in V, so C1 times U1 is also going to be in V. And all of my CK times UK are going to be in V. And since V is closed under vector addition, right, V is a vector space and all vector spaces are closed under vector addition, then if I add C1U1, which is in V, plus C2U2, which is in V, and all the way through to CNUN, which is also in V, I get something in vector space V. Right? For any V in the span of U, that V is also in vector space V because you can choose the way to write it out. And that's the definition of a subset. Everything in span of U is also in V, so span of U is a subset of V. Right. I like going through those two properties on their own because they give you some sense of what we're talking about with the span of V, but the real thing we're looking at here is that the span of U is a subspace of V. We have span of U is a subset of V. We have span of U is non-empty. Those are two important properties of a subspace. But the ones that we want to worry about are the closure properties. vector v and vector w are going to be two elements in the span of U. Using the definition of span of U, that means we have a bunch of coefficients a1 through an and b1 through bn. And if I want to add these together, well, I will get a1u1 through to an plus b1u1 through to bnun. But all of these things are elements of the vector space V. And vector addition in vector space V must be commutative and associative, which means I can rearrange this. And get a1u1 plus b1u1 together, and get a2u2 plus b2u2 together, and all the way down until I get anun plus bnun all together. Right? Using the commutative and associative properties of vector addition, we can drop the original parentheses, we can reorder everything, and we can introduce new parentheses. Then, using the distributive property of scalar multiplication in vector space V, I know that this is a1 plus b1 times u1, and a2 plus b2 times u2, and all the way down to an plus bn times un. That's a scalar. That's a scalar. That's a scalar. We could write this as c1u1 plus c2u2 plus cnun, which is very obviously in the span of U. Scalar multiplication is going to work pretty much the same way. We have a distributive property for vector addition and scalar multiplication in vector space V, and all this stuff is in vector space V. And we have an associative property for scalar multiplication and multiplication of scalars in vector space V. And so we have a bunch of scalar constants times our vectors. This is another linear combination, so we are in the span. And those two things are what it takes to show that the span of a set of vectors is a vector space. All right. Let's take a look at a slightly more concrete example. I want to take a set of real vectors, and specifically the set of the unit vectors in the Euclidean space Rn. So I've got all of them in n-dimensional space. So that's one bunch of zeros, 0, 1, 0, 0, 0, 0 through to 0, 1 as all of my unit vectors for Rn. And by the theorem that we were just looking at, we know that the span of this thing is a subspace of Rn. In fact, what I want to show is something a little bit more powerful, that the span of this vector space is equal to Rn. Since span of V is a subspace of Rn, we've already established that we have the same operations for vector addition and scalar multiplication. So all we have to show is that the sets themselves are equal to each other. In set theory, the definition of set equality is that A is equal to B if and only if A is a subset of B and B is also a subset of A. One direction is pretty easy. Span of V is a subset of Rn. So that means that the only thing we want to show here is that Rn is a subset of the span of V. To show that one set is a subset of the other, let's take some vector V as an element of Rn. I guess talking about elements of the Euclidean vector space, we usually call them X. So let's stick with that. And we know what the Euclidean space Rn looks like. It's the column vector of x1, x2, down to xn. Now we've seen in the past, we've used this trick before, that is equal to x1 times 1, 0 to the 0, and x2 times 0, 1 down to 0, until we get down to xn times a bunch of zeros, 1. Picking any vector in Rn, we can write it as a linear combination of the unit vectors e1 through to en. The span of V is defined as the linear combinations of e1 through to en. And since any arbitrary element of Rn is also an element of the span of V. That means that Rn must be a subset of span V. And since we also had already established that span V is a subset of Rn, subset inclusion both ways is the definition of set equality. There we have it. Pretty much for the rest of this unit, we're going to be looking at the idea of a span of a set of vectors and establishing some more properties, some more things we can analyze about a vector space by figuring out sets that can span that vector space. It's one of the most useful properties we have in linear algebra, this idea of the span of a set of vectors, and we can represent a vector space using the span of a set of vectors. For now, I would like you to take some time to work through the practice problems on the span of a vector space, and I'll see you next week for the next video.